This is the next class, and we'll be generally moving to the topic of problem solving. So, how do we carry out problem solving in any general problem? So, it's a sort of a solution for any type of problem that we have. We can use this, what is called the general problem solving methods. So, what is done here is that we find the solution by method of search. So, how do we carry out this search? We have a state. So, you have a state in which the problem is there at the beginning, and we know the state when we reach the goal. So, the idea is to move from one state to another state till we reach the state which is your goal state. So, that's the basic idea here. And then each movement from one state to another is by doing some action or using some operator to move from one state to another state. So, basically you will get a path which is there from the start state to the goal state, and this path actually gives you your solution. So, in other words, you get a series of actions which you need to carry out so that you can go from the start state to the goal state. So, your solution will be a fixed sequence of actions. So, this is of course by the method of search, like I said, and there are a number of strategies which you use for search. But what we will see now is the general method of search. How do we formulate the problem, and how do we see whether the problem that we have is suitable for the type of search that can be carried out. So, basically we have a goal formulation which is based on the state in which we are and some performance measure that we have, and using this we formulate what is called the goal state. And so when we formulate the problem, we have to decide which are the states that we have. So, what is the state and what is the action, and also the transition from the state to the action. So, if I am in a particular state, what is the action I have to carry out to go to some other state? So, these things you will have to fix. And once you fix this problem, then you can use a search algorithm to carry out this problem and come up with the action sequence. So, that's the basic idea. So, let us define the problem. How do we sort of define or get the problem definition over here? So, first of all, we have to say what is the initial state, that is the state in which the agent starts, and a description of all the possible actions that can be taken by the agent. So, suppose you are in a particular state S, then action S, if you give, it returns all the actions that are possible for the agent to do from that state S. So, you get what is called the transition model, which is specified by the function result SA. In other words, if you are in state S and you carry out action A, then what is the result of that? So, what you get is a new state, the successor state. So, every state that is generated at any particular point in time will have to be tested to see whether it is the goal state or not. So, they do what is called the goal test. Of course, that depends on the goal, right? So, you just have to compare and see whether the state is your goal state or not. And is there any cost that is involved? Yeah, so you have what is called the path cost. So, we know that it's a path from the initial state, from the start state to the goal state, you have a path, and you will have a path cost. So, the cost, I mean each action will have a cost. So, if you put all those together, you will get what is called the path cost, and maybe the idea is to get the solution with the optimal path cost. So the optimal solution will have the lowest path cost. There may be a number of different ways of solving the same problem, and if that is the case, then which is the one which has the optimal path cost? So that is what we have to see. And if you take the initial state, all the action, transition, model, everything, you get what is called the state space. So the state space of the problem, that is all the states that are reachable starting from the start state with the actions that you have, the whole thing is known as a state space. And the state space will consist of number of paths, which consists of each path consists of a sequence of states connected by sequence of actions. So this whole thing is known as the state space. So what you are trying to do is you are going to generate the state space. So maybe fully or maybe partially you generate the state space, and from that state space which has been generated, you find the path which will give you the sequence of actions to be taken to reach your goal. So that is what we are doing in the case of the problem solving. So first of all we need to define the problem. We'll go later into how we carry out the search algorithm and what are the different type of search algorithms that are available, etc. But first let us define a few problems, okay, so that it will give an idea. So first we will talk about some toy problems where we can define the state space, and then we will go into some real problems, and then we'll see how we actually generate the state space that is required to find the solution. So the first problem that we will study is what is known as the vacuum world. So we have already seen this a little earlier where we spoke about vacuum cleaner which is there, and there are two rooms, and you have the vacuum cleaner located say in room A, and room A could be either clean or it can be clean or it could have dirt, and you have room B which can also be clean or it can have dirt. So these are the variations that we have. So the state, actually a state will consist of room A and room B, and you will have the location of the agent. Okay, so the agent will be located either in room A or room B, and the location of the dirt, which could be either in room A or it could be in room B or it could be in both, or it may not be in either of the rooms. Okay, so that is what will define a state. So what are the number of states that we can have? So there are two rooms, and each room can be either clean or it can be dirty. So if you look at it, you see that the total number of states you have is 8 states. Okay, and if we say have n locations, okay, instead of 2 rooms, if you have n rooms, so you'll have n into 2 to the n. So that will be the number of states that you have in your particular problem. So this of course is a toy problem. You won't consider doing this only for 2 rooms, but you can also consider this for something bigger. We will just see it for 2 rooms just to understand what is happening. So what is the initial state here? The initial state could be anything. The vacuum cleaner may be in room A, and there may be dirt in room A, and there may not be dirt in room B. So that could be one state. So in this way it could be any of the possible states or any of the 8 possible states we spoke of earlier. And what is the action that can be taken? So there are basically 3 actions. Either the vacuum cleaner can go left, or the vacuum cleaner can go right, or it can suck the dirt. Okay, so these are the 3 actions that we are thinking of. If you have a larger environment, for example, you can have like a 2-dimensional like a square where you have rooms. Okay, so you may also have to have up and down. Okay, so you may have more number of actions that are possible. It can be left, right, up, down, and suck. Okay, so that is in the case of bigger environments. And what is the goal test? It has to check that there is no dirt in room A and in room B. In other words, if there are more squares, all the squares should be clean. That's the basic cost. And what is the path cost? Each step costs 1. Okay, so each action that the vacuum cleaner takes will have a cost of 1 or a step cost of 1, and you can count the number of steps to see what is the path cost over there. Okay. For example, suppose it is in room A, okay, and there's dirt in room A and there's dirt in room B. If it first goes to room B and then it cleans room B and then comes back to room A and cleans room A, it will be actually the path cost will be higher than if it first cleans room A then goes to room B. So it depends on the number of steps that are taken. So that is one problem. So I will only talk about different problem formulations as of now, and later on we can go into how how to solve these things. So the next problem we'll consider is what is called the 8 puzzle. Okay. So what you have is a 3 by 3 board. So you have like 3 by 3, so 9 squares are there, and you have numbered tiles. So you have tiles numbered from 1 to 8. So you have in each square you have one tile with some number on it, and there's one blank space, and it's possible for you to move the adjacent tiles to that blank space, or you can slide it into that space. Okay, and the object is to reach a specified goal state. So let us see how this works. So if we look at this here, okay, so this could be your start state. Okay, so we have a number of tiles and we have the blank space in the middle, and this could be your goal state. And what is possible is you can move 6 to the blank space, or you can move 5 to the blank space, you can move 3 here, you can move 2 here, etc. And then from that position you have a new configuration or a new state, and again wherever the blank is you can move the tiles into that blank space, and you keep doing that till you get this goal state. Okay, so that's the basic thing we are trying to do here. So let us formulate the problem. What is a state? So a state could be a 3 by 3 board, okay, with the 8 tiles in it and one blank. Okay, so the 8 tiles could be in any position, in any location, and then you have the one blank which is one of the 9 squares. And what is the initial state? It is one designated state. For example, here we have the start state given to us, so that would be your start state. So you have one state in which it starts, so that would be your start state. And what is the action that can be done? Of course, you can think of it as moving tiles into the empty space, but it's easier to think of it as moving the blank space, because that makes it more general. Okay, so you don't have to worry about what tiles are saying that this particular tile needs to be moved, etc. So whenever you have a blank space, the blank space can be moved either left, right, up or down. So there are 4 possible actions: left, right, up and down. And some of these actions may not work. For example, if you are already at the right end, if you say move right, then no operation takes place. So and if you are right on the top, you cannot move to the more to the top, etc. So you have a subset of left, right, up and down. Okay, so these are the actions which can be taken, or these are the operations that you can use. Then what is the goal test? The goal test would be to check whether the configuration matches your final configuration which you are looking for. Okay, so if it matches, then your job is done. Okay, so that's the thing. And what is the path cost? Each movement that is made, or each action or each step, has a cost of 1. So the path cost will be the number of steps that you require to move from the initial state to the goal state. So that would be your path cost. And the transition model, given a state and the model, it returns another resulting state basically. Okay. So this is the formulation of the 8 puzzle. And if you look at the 8 puzzle, since you have 9 squares, okay, what are the number of states that are reachable? You have 181,440 states, okay. So those are the number of states that are reachable, and this puzzle can be done fairly fast, okay. But you can also extend this puzzle and make it into a 4x4 board, which is known as the 15 puzzle. So if you take that 15 puzzle, you have 1.3 trillion states. So obviously it's a much bigger problem than if you take the 8 puzzle, okay. And like they say, it can be solved in a few milliseconds, right? So it's possible to solve it. And if you take a 5x5 board, okay, which is known as the 24 puzzle, it has 10 to the 25 states, and it takes several hours to solve this. So obviously as you increase the size of the board, the complications increase, the number of states increase, and it takes much longer to solve this puzzle. Okay, next problem that we consider is what is called the 8 queens problem. So if you have a chess board of say 8 by 8, then you need to keep the queens on the chess board so that no queen attacks any other queen, okay, which means a queen is attacked by another queen if you have another queen in the same row, same column or same diagonal, okay. So you have to place the queen so that you don't have any, if you place one queen, then there shouldn't be any other queen in the same row, in the same column or in the same diagonal. So this is what this problem is about, and here you can see that whatever has been put here, okay, this is not a proper solution because this queen is being attacked by this queen, right? As soon as if you start putting the queens from the left, by the time you put this queen here, this queen is attacked by this queen. So this is not a proper solution, but almost like till here it's fine, right? So one or two more things are necessary to be done over here, okay. So how do we do this? By using the problem solving methods, okay. So like they say, there are two types of formulation, incremental formulation and complete state formulation. So it depends on what you are trying to use. So if we look at the increment formulation, we can say that we start putting queens on the board, okay, from the left column and move towards the right, okay. And every time we put a queen on a particular column, we try to put it such that it is not attacked by any queen before that, right? And here we are not worried about the path cost because we only want the final state, so the path cost is of no interest over here. So what is the definition of all these things? So what is the state here? Any arrangement of 0 to 8 queens on the board. So it could be just having no queens on the board. You start with no queens on the board. Then you have say 1 queen on the board, 2 queens on the board, 3 queens on the board, etc. So any arrangement of any n number of queens which is less than 8, less than or equal to 8, right? So that is what you say. And the initial state will be just the chessboard with no queen on it, okay? And what is the action? Action is to add 1 queen to any empty square which is there. And the transition model returns the board with the queen added to a specified square, And what is your goal test? You see if there are 8 queens on the board and you see that no queen is attacking any other queen. So this is the formulation as far as the incremental formulation is concerned. Okay. So how many possible sequences is there to investigate? Since you have 64 squares, okay, you have 1.8 into 10 to the power of 14 possible sequences to investigate. Okay. So what you can do is, like they say, you can use a formulation which will prohibit placing a queen in any square that is already attacked. Okay. So once you keep one queen, say in one square, you know the squares where you cannot keep the next queen. Okay, so you can mark those. Okay, and see that you keep them only in the other squares. So and you prohibit the placing of the queen in any square that is already attacked. So because of this, it will maybe reduce the complexity to some extent. So what are the states? All possible arrangements of n queens, one per column, in the leftmost n columns, okay, with no queen attacking another. So you start from the left and you keep adding the queens, okay, one per column from the left to the right, and every time you add a queen you see that it is not attacked. And what is the action? Action is to add a queen to any square in the leftmost empty column, okay, such that it is not attacked by any other queen that has already been placed there. Okay. So this is the formulation. Okay. And this formulation reduces the state space from 1.8 into 10 to 14 to just 2057 sequences, okay, making it much easier. So if you increase n, okay, if you suppose you talk about this as the n queens problem, right? We have used a small n, so let's say capital n queens problem. Then if as you keep increasing n, it becomes more and more complicated. So they say that for 100 queens, the reduction is from 10 to the 400 to 10 to the 52 states, which is a lot of reduction. Okay, so it depends on how we formulate the problem. Another way to formulate could be that you take all the 8 queens and you place them in one column each, okay, somewhere in one column. And then each action could be moving one queen which is attacked to another square in the same column. Okay, so that is also another formulation. So here a state would be 8 queens which are on the board, one in each column. Okay, so and finally it would be 8 queens which are on the board, none attacking any other queen. So this is how we first formulate the problem. So we need to formulate it before we actually carry it out. Okay. Now this is what is called the cryptarithmetic problem. So here what is it that we are doing? We have an arithmetic problem which consists of letters, okay, not numbers but letters. So we have 40 plus 10 plus 10 which gives 60. So the idea is to find a corresponding digit to each of these letters. Okay, so T will have one digit, E will have one digit, N will have one digit, etc., which is between 0 and 9, and no two alphabets can have the same number, okay, be associated with the same number. They all have to be associated with different numbers. Okay, so this is actually a solution to this problem. So 40 plus 10 plus 10, this could be the formulation. 40 plus 10 plus 10 is equal to 60. Okay, so we'll see how to solve the cryptarithmetic problem later on. Okay, so let us look at the formulation now. What is a state? Okay, a state is some letters which are associated with some numbers and some letters which are not, right? You also have unassigned letters. And the initial state, you have all the letters are unassigned at that point in time basically, okay. And an action is to assign a unique unassigned number to a letter, okay, so that the rules of arithmetic are followed. And what is the state transition? If k letters have been assigned numbers, assign an unused number to the k plus 1th letter, okay. And the goal state is that all the letters have been assigned numbers which are unique and the rules of arithmetic are satisfied. So that is the basic idea of the script arithmetic problem. So usually you use what is called the depth first search algorithm here, and what makes this easier is the constraints that you already have. So you have constraints which say that the letters have to have numbers between 0 and 9 and all of them have to be unique and they have to follow the rules of arithmetic. So when you put all these constraints into it, you find that it reduces the number of possible values that these variables can take. Okay, so you try to make use of that to simplify the problem of finding the assignments which we are looking for basically. Okay. Another one or two problems which I wanted to talk about is you have the Tower of Hanoi problem. So in the Tower of Hanoi you have 3 discs. And in the first disc, you have 3 pegs, and in each peg, in the first peg you have 3 discs. In this way, you have 3 discs which are put into that peg, and these 2 are empty. Okay, so this is your starting point, and your final goal is to have these 2 pegs empty, and this one will have the 3 discs on it in this way. Okay, so this is peg A, peg B, peg C. Here also we have peg A, peg B and peg C. And we have some constraints here also. So basically how you do it is you can take out one of the discs and put it into one of the other pegs. But some constraint which is there is that you can't put a bigger disc on top of a smaller disc. Okay, so that is a constraint that you have, and you can have a state which you do here. The state would be something like first of all it would be like it will be having 3, 6, 9 values. Okay, so the first 3 values would be whether let's call this say disk 1, disk 2 and disk 3, whether disk 1 is there, disk 2 is there, or disk 3 is there. So 1, 2, 3, it will be 0 if the disk is not there, okay, or it will be 1 if the disk is there, okay, and same thing for B and same thing for C. So that could be your state, okay, and the new state would be to have these things moved around, right? So your initial state would be something like 1, 1, 1 here, and the rest will be 0, and your final state would be 1, 1, 1. Okay, so this is your goal state. Okay, this is your start state. So this is how you formulate this particular problem. Another thing you have is something like you have a 8 liters jug and you have a 5-liter jug, okay, and you can fill them with water, and what you want finally is 4 liters of water. Okay, so how do you go about doing that, right? So your state formulation could be like, you could have a tuple which says how many liters, say the 8 liter has in it. So maybe at the beginning 8 liters would have 8 liters and the 5 liters would have 0 in it. And then if you move that from the 8 liters, if you move 5 liters into this, you would have 3 liters here and 5 liters here, etc. Right? So what you want is 4 liters. So how do you, what is the steps that you need to go about doing it? Another problem we have is something like 8 liters, 5 liters and 3 liters, I think. So you have 8 liters, you have 8 liters already present in this and 0 in these two. And what you want is something like 4 liters in this, 4 liters in this, and 0 in this. Okay, so this is the 8 liter, the 5 liter, 3 liters, 1. Okay, so this is another formulation which you can think of. Again, you can have a state which consists of these three and the now amount of water which is there in the particular jug. Another formulation you have is something like, you have a farmer, another problem, and the farmer has a wolf, sheep, one sheep, and a cabbage, and you have a river, okay, and he wants to cross over to the other side of the river, and he has a boat, okay, and in the boat he can sit in the boat and he can have only one other item with him, and he can't leave the wolf and the sheep unattended because the wolf will eat the sheep, and he can't leave the sheep and the cabbage unattended because the sheep will eat the cabbage, etc. Okay, so you have to find a solution for the farmer to cross over to the other side with all these three items. Okay, and your final state would be something like having the farmer here on this side, the wolf on this side, the sheep on this side, and the cabbage on this side. Okay, so that is your final thing, and your state could be something like, you can say like, if you consider the left side of the river, okay, if the farmer is there on the left side, you have 1. If the wolf is there on the left side, if the sheep is there on the left side, cabbage is there on the left side, 1, 1, 1, 1. And you could have something here which says either they are on the left side of the farmer is either on the left bank or on the right bank. So you have left or right, one thing which tells you, right? And the action could be to go from the left to the right with certain items in the boat, right? So these are some toy problems which we are basically talking about. So I will stop at this point, okay, and we'll continue with some real world problems, okay, in the next session. Thank you.